Okay? So, part 2 of the concavity, points of inflection. After we find the first derivative, we find the second derivative. Okay? And again, you're just going to come up to the second derivative, and this is going to be an expression. Any x values that make this expression positive, those are the x values we're looking for. And of course, we have a inequality, so we're going to have a whole range of x values, right? Maybe not just one, we'll have a whole bunch. And of course, when you solve for this is very simple. There's no squares or anything, this is just degree 1 here. You have x greater than 1. So if you plug any value that's greater than 1 into the second derivative, you should yield a positive answer. We could just do a quick brain check there. Okay, greater than 1, so 2. 6 times 2 is 12, minus 6 is positive 6. Good. You can do as many as you want, they'll all be positive. Awesome. You can check the opposite too, like 0 is less than 1. 6 times 0 minus 6 is a negative number. Okay, we're good. So what that means is that this function right here is concave up whenever x is between 1 and infinity. Okay? So now I'll just kind of point out these are rounded brackets here because this is greater than 1. Okay? We're not necessarily interested in the exact value. So I think the protocol here is always to kind of use round brackets to not include that, but in between. Okay? If you find an example where that's changed, they use square brackets on the interval to close that off, then let me know. But the bottom line is this is the interval we're looking for. Okay? Now, it's concave down, just as a side note. If you're asked for where is this concave down, well, it's wherever the second derivative is negative, and that would be between negative infinity and 1. Questions on that? Okay. Now, the points of inflection. Now, we talked about the points of inflection. This is where it changes. If we are able to determine, okay, where the second derivative is positive, and then if we have another section where it's negative, the changeover point is the point of inflection. So, the point at which the concavity changes is the point of inflection. You may have this in your notes already from before, but inflection. And it always is stated as a point too. It's not really stated as, hey, x equals some value, that's it. No. It's stated as a point. So what that means is that you're going to have to state it as an xy coordinate on the function. So you're going to find x pretty easy, but you have to solve for y. You have to plug that x into the original equation, solve for y to get the 2 coordinates for the point. Okay? So it's stated as a point. Questions? Okay, point of inflection. I think, yeah, I'll just kind of skip that. Okay, I'm going to direct you to example 2 in the textbook, okay, if you follow along in class. And it basically, example 2 says, okay, there's actually some terminology here that we need to cover. First of all, it says, discuss, this is the first time you've seen this, discuss the curve, it says. Discuss the curve, and it gives you the equation, with respect to concavity and points of inflection. Okay. When you see the word discuss, okay, that is something that you're not probably used to seeing in math. In calculus, it's mentioned all the time, and what it means is, it means basically define, describe, tell us all about. That's what discuss means. Tell us all about the curve, and what I want to know about it is the concavity. So instead of saying, tell me at exactly what x values the graph is concave up and concave down, and also tell me what all the points of inflection are, it just says, hey, discuss concavity and points of inflection. Okay? So there's just some terminology that you'll see, and you'll say, discuss. What does that mean? Do I have to write a paragraph? No. Just do the math, and that's what it means. Do the math and find out tell everything you know about the concavity, you know, the interval, all that stuff, where it's positive, negative, give the points of inflection, etc. Okay? So that's number one. Now, in this example in the textbook, you see that they actually give you a function, y equals. Okay? So finding the second derivative is not the point of this section. Okay? So that's why we're not going to do it here right now in this lesson. But if you want to look at the textbook to refresh yourself how to find second derivative, this is the second derivative that you end up getting from that function. Okay? And the function is x over x squared plus 1. This is the original one, x over x squared plus 1. Okay, so find first derivative, then find the second derivative. You should get this. The point of this lesson is, what do I do with this second derivative now that I have it, right? Okay? First thing is first. You want to try and factor, okay, as much as possible, or identify factors in this, because we're going to do sign analysis. Do you remember sign analysis? Okay? Because there are going to be several points of inflection here, and therefore there may be several sections of this graph where the concavity changes. Okay? All right, so sign analysis. You put your factors on the left side here. This may be a review if you've totally forgotten this. This is another factor, and this is just one factor. And you don't have to put each factor separately if you don't want to, which I'll show you in a second here. But this is a factor, x squared minus 3. We'll deal with this in a second. And I like to put a little divided sign here just so I remember where things are 0 and where they're undefined. Okay? So I put a little divided sign here because we have factors in the bottom. Now, how do we deal with this? Oh, it's cubed. Okay, well, for some values, and this x is squared and everything, some values, it's positive, some it's negative. How do we figure that out? Here's a little hint. This is what I would probably do. Write this as x squared plus 1 squared. And then write a separate one as x squared plus 1, just to the positive 1. Okay? If you write it like this, you're going to see something. And you may have seen it before. I don't know. You may have seen this before. But if you know, this is squared, right? This is squared, so that means that it is positive everywhere. Is there an x value where this is 0? Because remember in sign analysis, that's kind of what we're looking for. Is there an x value where this is 0? So x squared plus 1 equals 0. Or what value of x when squared equals negative 1? Okay? Is there a value for x that when you square it gives you negative 1? No. No, we're not doing complex numbers or anything, so no. So this is positive all the time. Okay? And if you look over here now, and this may be just easier to see, but hey, if you have a x value, no matter what it is, and you square it, that's going to be positive in there, right? And if you add 1 to an already positive number, you're never going to get a negative. So this is actually positive everywhere as well. The only thing you would check for is, hey, is there an x value that makes this 0? And again, you would say the same logic here, x squared plus 1 equals 0. What value for x when squared gives you a negative 1? There is none. So actually, this is positive everywhere, this whole denominator, but you might not see that right away. Okay? If you were smart enough to see that before we did all this, good on you. Okay? Great job. Let's focus on the top then, real quick. Okay? Keep moving on here. So x, we know x is 0 at 0, right? And because this is a positive term, if x was less than 0, that would make 2x negative. And if x is greater than 0, that would make 2x positive. Good? All right. Now, this one's a bit tricky. This one's a bit tricky. This one's a bit tricky. Now, why is this tricky? Because there are x values where this whole thing is positive, and there are some x values where this whole thing is negative. Does anyone see how I might want to break this one down? Because I actually want to break this one down even further. But it's not strikingly obvious right now. I'll be honest with you. I wouldn't expect it to be real obvious. Okay? What does this format sort of look like? What does this look like? Ah, it looks like a difference of squares. Right. Now, would we have classed this as a difference of squares before? What? No, we would have said It's not a difference of squares because, yes, this is a perfect square, but that's not a perfect square. But you know what? Anything in this format is a difference of squares. Because is there a square root to 3? Yeah. What is it? Root 3. Yay! Hey, you're not restricted to perfect squares anymore. You guys have grown up. That's so awesome. Okay, so what you can do is if you want to help yourself out, and again, I would suggest this. I'm just going to make myself some room here, okay? Just don't get mad at me. I'm going to get rid of this. But what I might suggest that you do is break that up into its factors. So that's x plus root 3 and x minus root 3. Because the square root of x squared is x, the square root of 3 is root 3. Are you with me? Yeah? You picking up what I'm putting down here? Okay. Where is this 0? At x equals negative root 3. Negative ahead of that, positive after. Again, sign analysis here. This is 0 at x equals positive root 3. That's where it's 0. And sorry if you don't have enough room there all of a sudden. I just squished those two in there. Right? You could actually just go from here, I guess. You really could. You could go x squared equals 3. X equals plus or minus, root 3, and those are your roots. And then you could figure out, hey, if x is 0, what's that going to be? Positive or negative? Well, it's going to be negative. If x is beyond this, but this is easier, I think. Okay. All right, so to simplify things here now, let's get rid of these positives. You can leave yours, but I'm just so we can see this a bit easier. And now you do sign analysis, and of course, what you're left with down here is going to be the value, or the sign, S-I-G-N, of the second derivative. So we have negative times negative times negative. That's negative. This is all 0 here. Negative times negative. That's going to be positive. 0. This is going to be negative, 0, and positive. Okay, did I do that right? Does that look okay to you? And so we can see the concavity. So we'll just identify this just on the graph here. This is concave down. You see that? Wherever x is less than negative root 3. This is also concave down here where it's negative. And then we have concave up here and concave up here. Okay, so we see, okay, the intervals where it's concave up and concave down, and of course we could say that concave down. Just real quick, concave down is going to be on the interval of negative infinity to negative root 3. And then I like to use this little set notation, sort of in union with. That means or, right? Or 0 to root 3. That's where it's concave down. See the negative points there? The negative sections. And concave up, and I'll let you just do CU, is between negative root 3 and 0. Also in union with positive root 3 to infinity there. Okay? So those are the sections of concavity, and you can just state them like that. Okay? Just like that, that's good. If the book does it a little bit different and you want to express it a bit different, that's fine. Okay. Now, the points of inflection, all right? Just one more matter here with the points of inflection. Remember we said that those have to be written as points, not just x equals. And so we know that concavity changes, just like we look at the graph, or the sign analysis here, and concavity changes here at negative root 3. It goes from negative to positive, changes. So this is the x value for a point of inflection. Also changes here, right? And it changes here. So looks like we're going to have 3 points of inflection, and we know the x values from our sign analysis right there. And so what you're going to do, and I won't actually do it with you here, I'll just tell you how to do it, but you insert those x values into the original equation to find the y coordinates that go along with it. So you understand that if we have an x value, if you're looking for a point on the graph, insert that x value into the equation, solve for y, and that is the partner value, right, or the coordinate that goes along with that x. to describe a point on the function.